Well, I'll say good morning to everyone. There's old homework here that you can pick up after class. Also, I will not be here on Thursday. I have to go to the great city of Cleveland, Ohio, followed by a trip to Washington, D.C. So I'm going to be recording Thursday's class this afternoon at 2 o'clock in the other classroom. If anyone's available, you can come to that, or you can come back here on Thursday and it will be shown on Thursday. So the last topic I was talking about last class was phase unwrapping, and I want to go over this real fast again, and I have a couple additional comments to make on it. So the problem we're solving here is that we're calculating the tangent of the phase, and when we do the arctangent, we're getting the phase over a span of 2 pi. And so if we're measuring a surface that the phase distribution is greater than 2 pi, we're going to see steps in the measured phase like we see here. So the phase would go from 0 up to 2 pi and then drop down to 0, back up 2 pi and so on. And so we have to correct for these phase discontinuities. And often this is called unwrapping the phase. And so the approach, as we were saying last class, is that we're going to put a restriction on the slope of the wavefront being measured. And this is a restriction that we'll see several times during the course, and we'll try to come up with some techniques for getting around this restriction later on in the course. But the restriction is going to be that the phase between adjacent pixels can change, or has to change by less than pi. And if that is true, so we know that the phase between adjacent pixels is less than pi, then what we can do is we can look at the phase difference between adjacent pixels. And whenever the phase jumps more than pi, we're going to add or subtract some multiple numbers of 2 pi. So the phase difference between adjacent pixels is always less than pi. And so we'll take a wavefront, a measured wavefront that may look like this, and we'll fix these jumps in the phase. And so we'll end up with something like this. And so we can get a nice measured phase. So this is setting a limitation on the slope of the wavefront being measured. The problems come into play when you do this in practice is that you always have a little noise, and that noise may throw you over the pi jump, or maybe when you're supposed to go over the pi, maybe it will keep you from going over the pi. And so you'll get some errors when you go through this correction. Also, if you're testing something with holes in the aperture, or spiders, which are a real problem, we have to jump some way across the spiders. You need some type of intelligent unwrapping procedure here. Over the years, I mean, we've spent a lot of time working on this. Anyone who sells phase shifting interferometers has spent a tremendous amount of time on coming up with their particular algorithms for doing the unwrapping. And probably the one thing that we have learned that helps the most is that you first go over the aperture and you look at what the modulation is at the different points in the aperture. And you do the unwrapping on the high modulation points first. And then you work your way down. And only at the end do you do the unwrapping on the low modulation points. And that seems to reduce the errors that you get. Typically what you'll see, the errors are little streaks of discontinuities in the measured or calculated phase. And by doing the high modulation points first, generally you can make these streaks smaller, fewer number of pixels that are incorrect. Anyway, it can be a challenging exercise to do a good job, especially on noisy data. And I think I mentioned last class that there was this book. It's really a superb book, inch thick or so, talking about phase unwrapping. And if you ever get involved in doing phase unwrapping, I strongly recommend that you get a copy of this book. Okay, so we had said that last class. I just wanted to repeat a little bit here about doing the high modulation points first, because that can generally help you a lot. So the next topic on our list here is on phase shifter calibration. So all of these systems have some type of a phase shifter or frequency shifter. And we said we want to generally use 90 degrees phase steps, but it doesn't have to be 90 degrees, but the algebra generally becomes easier if it is. And so we'd like to some way determine just what the phase step is and adjust a phase shifter to make the phase shift whatever it is we want. As I say, normally 90 degrees. There are, if you go in the literature, you'll find several calibration procedures that people have described in the literature. But the one that I think most people use is this one right here. And the idea is we're going to take 5 frames of data, of irradiance data, where the phase shifts hopefully are close to 90 degrees, but where the phase shifts are -2 alpha, minus alpha, 0, alpha, and 2 alpha. And then you can show that the phase shift alpha comes from the equation arc cosine of 1/2 I5 minus I1 divided by I4 minus I2. Now, I don't have the derivation of this in the PowerPoint presentation here, but it is up on the web, and I wanted to go to it here. And so these are our notes on the web, and what I was just showing is this presentation here. And down here we have additional notes, and there's one down here called phase shifting interferometry. And let me go to that. So this is a Mathematica notebook, or a PDF of a Mathematica notebook, that I do a lot of calculations on phase shifting, and I do a lot of backup material to what is in the PowerPoint presentation. If we go down here to someplace, I don't know if I can find it here. Well, now I can't find it here. I'll find it later in the notes here. Should be phase shift calibration. Maybe it's down here.
7.8.
What is it?
7.8.
Ah, way down there, 7.8. Okay, good, thanks. So it's I knew it was way down here someplace. Oh, we'll come down here to, oops, not quite that far. Okay, so 7.8. So we said in last class that we can write the irradiance here in terms of an A0 plus an A1 cosine delta plus an A2 sine delta. And remember that the phase then turns out to be what we get from minus A2, or the tangent of the phase, minus A2 over A1. Anyway, that's just another way of writing our irradiance that we measure here. And we said we have these 5 phase shifts, -2 alpha, minus alpha, 0 alpha, and 2 alpha. And if I take the 5th one and subtract from that the 1st one, and you go through the algebra here, what you're going to end up with is 2A2 sine of alpha. Well, 2A2 sine of 2 alpha, I should say. And if we take the 4th one minus the 2nd one, you'll get a 2A2 sine of alpha. So here's sine of 2 alpha, this is sine of alpha. And then if we simply take the 1/2 of I5 minus I1 over I4 minus I2, it's going to drop right out that this is equal to the cosine of alpha, the phase shift. And so that would be our expression here. Now the sine of what we have up here, so cosine of alpha is this mess right here. So the sine of what we have up here tells us whether alpha is too large or too small. So we know which way we have to change it. Now, that's all I wanted to show you here. And the main reason I wanted to show you is to point out this other set of notes that has a lot of additional backup material on phase shifting. So now I'll go back. I mean, I have more words here, but I think I have the same words here on the PowerPoint. So we say that this is our calculation of alpha. And if we look at the sine of the I5 minus I1, that will tell us if alpha is too large or too small. Now the problem here is that you have some singularities. And I didn't show that right back. I should go back and I should point out something right here. You know, we have a problem here. Remember that A1 and A2 depend upon what the phase is that we're measuring. And so we could be measuring a phase where A2 is equal to 0, in which case we kind of have a problem here. So how do we get around that particular problem? Well, what we normally do, if we're calibrating here, is that we will put in tilt fringes. So we have a lot of different values of phi. And so for some of these values of phi, this A2 is going to be equal to 0. And we're going to have singularities in this calculation here. But then what we do is we look at the numerator here, I5 minus I1. We look at the denominator, I4 minus I2. And whenever this is smaller than some threshold that we set, we throw those data points away. And we're going to use only the data points in this calculation here, such that I5 minus I1 is not close to 0 and I4 minus I2 is not close to 0. That turns out to be a very important thing to do. So we're doing this calculation here at, well, at each pixel, or at least at many, many pixels over the aperture. And we'll throw out the ones for which the numerator and denominator are too close to 0. And then we'll solve for alpha. Well, we're going to have many different values of alpha. I mean, ideally, alpha would be the same at every data point, but it's never exactly the same. You may have vibration, maybe your phase shifter is tilting or something as it moves along. And so then what we normally do is we make a histogram of these phase shifts. So we make a plot showing how many, well, we'll bin the data, and we'll make a plot showing how many data points given alpha within a certain value, and then how many data points give it within another certain value, and so on. Now this histogram should be pretty peaked. Alpha shouldn't vary much across the pupil. And if it does vary much across the pupil, we probably know that something is wrong with the system. And so do the histogram, fairly peaked, look at what the peak is, and that is what we'll use for alpha. Okay. Well, back in my WICO days, I mean, we had this in our software, and our competitors had it, something similar, maybe identical thing in their software. And the competitors used to have a sales pitch against us that they would measure the phase shift. Every time they took data, they'd measure what the phase shift was before they took the data. And that was their sales pitch. And my comment to that was, if you have to measure it every time you take data, there must be something wrong with your system. And so, I mean, in our case, we'd measure it once a week or once a month or something. It was stable enough. And I really think that's true. You shouldn't have to measure this very often, but every now and then you want to check to make sure that you have close to the right phase shift. Now, what if you don't have the right phase shift? Well, that's going to be in the next section here. So any questions on this? Okay. So that takes us to errors in phase shifting. I mean, phase shifting is certainly very, very powerful, wonderful technique, but it's not perfect. And so we're going to talk about 5 different sources of errors here. Errors due to stray reflections, and we're going to digitize the data a certain number of bits, and we want to know what error that causes. Should we really digitize to 8 bits, 10 bits, 12 bits, how many? Detector nonlinearities, source instabilities, maybe the intensity of the source is varying with time, maybe the frequency is varying with time. And then what we just talked about, the phase shift between data frames. What if we don't have the phase shift that we want? What if we don't have 90 degrees? So of these 5 error sources, the really 2 most common ones that cause the most trouble are the incorrect phase shifts between data frames and stray reflections in the system. Problems due to quantizing the data, detector nonlinearity, and source instabilities. I think we should say a few words about these. And there's a lot more words in the Mathematica notebook that I just showed you, but we'll say a few words here, and they're not going to be so important. So let's look at some of these errors. First one, stray reflections. And I've mentioned stray reflections many times already in this course. And the reason is that they're such a problem. They really can drive you crazy. And they're so easy to get stray reflections. So these stray reflections, I mean, when you use a laser, you have a long coherence length. And so all these stray reflections are probably coherent with respect to one another, and they give you interference fringes. And if you look in the literature, you can find quite a number of papers on stray reflections. And I mean, they really can be a problem. And but after thinking about it, I say, you know, the easiest way to think about a stray reflection and what it does to you is that the stray reflection adds to the test beam to give a new beam of some amplitude and phase. So, as I show down here in the drawing, let's say this is my test beam. So I represent it as a vector. So this is the amplitude of the test beam, and this here is the phase of the test beam. Now I have a stray reflection from something or another, and it has some amplitude, like this, and it has some phase, you know, so that I guess I drew it pretty much vertical, but it may go at whatever angle, you know. It has some phase. If the same phase as the test beam, that's not a problem. But if it's different from the test beam, then you have these 2 beams are adding and are coherent, so they're adding coherently. And so it makes it look like I have a beam that looks like this. So incorrect amplitude, which I probably don't care about, but it doesn't have the phase of the reference of the test beam. It has some different phase relative to the test beam. So this would be the total phase of it. And so what I'm really doing is I'm measuring a beam of the wrong phase. And so it's pretty hard to get rid of the effect of this stray reflection. Now, if when you're phase shifting, the phase of the stray reflection changes, then maybe you can do some tricky things, and there are papers on this of how you can maybe get rid of the effect of the stray reflection. But the problem is, too often the stray reflection, the phase of it does not change when you do phase shifting. And so there's not much you can do about it. So what can I do? Well, I'm going to design and fabricate my the interferometer in a way to minimize the stray reflection. And so that means, well, I hate to use AR coatings because I always complain they cost so much money. But I'll probably put in some high-quality anti-reflection coatings. But you really have to cut the reflection down by a tremendous amount because it's amplitudes that add. And so even if I cut if the stray reflection is 1%, intensity-wise, 1% of the test beam, when I do amplitudes, that's 10%. The amplitude is 10%. So you really have to cut down on the amplitude of the stray reflection a lot. Or you'll put in wedges or something and stops in the system. So you try to send the stray reflection off in some other direction. And so it's stopped someplace and doesn't get to the detector. Or the other technique, and we'll show some results for this before too long, where we're going to, instead of using a coherence, a laser of a very long coherence length, we're going to go to shorter coherence lengths. And that will cut down on, may not cut down on the stray reflections, but it will cut down on the interference fringes resulting from stray reflections. So in any case, this is, stray reflections are just a real bother, and especially if you're making instruments to sell, no one wants to see a stray reflection, the results of a stray reflection in the results when they look at the measured phase. So next is not such a serious problem, but it's the fact that we're going to digitize our data to some number of bits. And typically it's 8, 10, or 12 bits. So quantizing the data introduces some error also. And there's a wonderful paper here by a man by the name of Chris Brophy, that's in JOSA here, where he goes through and derives this expression here, which is, a derivation is pretty long and involved and makes a few assumptions, but the assumption seem to be okay. And so it says if I digitize something to B bits, and if I have an algorithm, phase shifting algorithm that has n steps, then the RMS phase error goes as 2 over 2 to the b, 2 to the number of bits, square root of 3n. So it depends a little bit on the number of steps you have, and the more steps you have, the smaller the error. But it goes as 1 over the square root here, so of the number of steps, so it doesn't make too much difference. And so if we think here, let's say we have 5 steps, and so 3 times 5 is 15, square root of 15 is about 4. And so the 4 here, 2 times 2, so 1, 2 goes away. So we end up with a phase error that goes as about RMS phase error, about 2 to the b plus 1. 1 over 2 to the b plus 1. And so this is in phase, radians, so divide by 2 pi to get waves error. And I think in these Mathematica, the other set of notes I showed you, I have a table showing what the RMS phase error is as a function number of bits. But as a typical number, let's say we use 8 bits and we use 5 steps. I have here that in units of waves, this turns out to be 0.0003 waves. So 0.3 over 1,000 waves for 8 bits and 5 steps. And every time I add another bit, that error goes down by a factor of 2. So 8 bits, 0.0003 waves. So I think, 8 bits is enough. Well, we used to sell interferometers having 8 bits, digitized 8 bits. Now we use 10 or 12 bits. Why did we go to more than 8 bits when it sounds like 8 would do it? Well, the whole thing is right down here in this sentence here, that if the fringe modulation spans a whole dynamic range of the detector, then probably 8 bits would be enough. But the problem is, well, maybe you don't have 100% coherence, so that reduces the fringe contrast. Maybe the two beams are not matched in intensity, so that reduces the fringe contrast. Maybe you don't have enough light, you didn't adjust the intensity just right, and so your data doesn't span the whole dynamic range of the detector. So the detector may have 8 bits of capability, but maybe your fringe data is only using 6 bits or 5 bits or something. And so it's really to your advantage to have a system that has 10 or 12 bits. And so now you don't have to be so careful about matching the intensities of the two beams or adjusting the intensity just right to use the entire dynamic range of the detector. And so I think that using 10 or 12 bits is at least from a user standpoint, using 10 or 12 bits is much safer. Okay. Now this last bullet here, it's kind of interesting. If a noise is greater than 1 bit, this error can be reduced by averaging data sets. So what that is saying, and I think it's really true, is that sometimes noise is good. Sometimes noise can help you. If it's really random noise, and that's what I've learned in doing a lot of phase shifting work, is random noise is kind of nice because you can average it out. And in this case, if our noise is real small, well, we're going to get the same measurement every time, and we're kind of stuck by whatever the number of bits are that we have. But if we have a little bit of noise, so this jumps around enough, then I actually can get better results in this if I average a lot of data. So sometimes a little noise is good. I think in real life, though, as long as you have 10 or 12 bits here to begin with, you probably don't even have to worry about this last item down here. But it's kind of interesting. Yes?
Sometimes you take, I guess, a lot of points when you continuously measure as you sweep PZT, let's say, if you're doing that kind of phase shifting. So what would you put in for N then? Is it still cut into kind of discrete steps even if you do a sweep?
Well, you may, you probably only read out your detector 4 or 5 times. You may, you're stepping your PZT a few hundred times maybe, but you're reading out the detector 4, 5, 6 times. So that's the N. It's the N that's in the particular algorithm, the number of steps in that algorithm. I have to mention something here about Chris Brophy. And Chris Brophy was an undergraduate here at the U of A and got a degree in physics. And his senior year, I was teaching Optics 505 at the time, and the senior year he signed up for 505, but after 2 or 3 weeks he dropped the course. So that's one strike against Chris Brophy. Then, when Chris graduated from U of A, what did he do? He went to graduate school at Rochester. 2 strikes against Chris Brophy. Okay. But then when he got his PhD at Rochester, by then I had gotten to know him a little bit, I ended up hiring him. He saved himself. I hired him to work for me at Wyco for quite a number of years. He was a really very bright guy. But the best thing, what I remember most about him, is that he was a superb athlete. In any sport you pick, he was the best. And in the Wyco days, we had this thing called corporate challenge, where different companies in Tucson once a year to have this athletic event where you would, all kinds of crazy things you would do in it. And we won that 4 years in a row for the city. And a lot of that was thanks to Chris Brophy, who could, whatever event we put him in, he would win it. So anyway, I have now forgiven him for dropping 505 and going to Rochester to graduate school. Also, I don't know, you don't even follow college sports here, I guess, so you certainly don't follow high school sports, do you? There's a school a high school in Phoenix called Brophy High, and that's named after his grandfather too. So, and they're very good in sports also. So anyway, anyone here from Arizona? Anyone ever hear of Brophy High School? No. Okay. Detector nonlinearity. That used to be a problem years ago, but it's not much of a problem anymore. Detectors, most of the detectors you'll use are very linear over their dynamic range, and so I'm not going to talk about it. There's a few notes on it in these Mathematica notebook I mentioned, but it's not a real problem anymore. Source instabilities. Well, we have two things to worry about here. We have the frequency of the source to worry about, and we have the intensity variations, or radiance variations. So remember, I mean, we talked about one phase shifter is that if we have a path difference in the interferometer, if we change the frequency of the source, we're going to change the phase shift, the phase. And so that's good if we want to do that, but if we don't want to do a phase shift by changing the frequency, it's bad. And so you just know that the phase goes as 2 pi times the path difference over the wavelength, which you can write as 2 pi d c over, and then times nu. And so if nu changes by delta nu, the phase changes by delta phi. And so this can be a problem if you have a large path difference between the two interfering beams. It's not often a problem, but it can be a problem. You can also show, I think I have more on this in the notes, that if n is the number of steps in the algorithm, that if you have a radiance variation with a standard it produces an error in the phase that goes as 1 over the signal to noise here divided by square root of n. And if you really get down to photon shot noise problems, which I dream about doing, always other noises that kill you before you get to that, that would simply go as 1 over the square root of the number of photons you detect. So anyway, source instabilities, in general, that's not a problem, not something you worry about too much. So let's get to what drives us absolutely crazy. As I said, stray reflections drive us crazy. The other is an incorrect phase shift. And the incorrect phase shift may come from the fact that we didn't calibrate our phase shifter right, or it may come from the fact that we have vibration in the system. And in those Mathematica notes that I mentioned earlier, or showed you earlier, I go through lots of calculations here using different algorithms to calculate the effect of what happens if you have an incorrect phase shift. And the thing that you always see, is that you're going to get an error in the measured phase that is twice the frequency of the original fringes. So if you say you put in 10 interference fringes in your interferogram, if you have an error in the phase shift, you're going to see a ripple in the measured wavefront of 20 cycles across the surface. It's going to be twice the number of fringes you have. And what I show here is, this is the phase that I'm measuring, and I'm showing it over a space of 2 pi, 360 degrees, and the error that I get is always, it's almost sinusoidal, very close to being sinusoidal, at twice the frequency. So as a phase measured goes over 2 pi, this will go over 4 pi, 2 cycles. So if there's anything you need to remember about phase shifting, I mean, this is it right here. You see this all the time if using a phase shift interferometer. Regardless how hard you try not to get it, you almost always see a little bit. I mean, it may be very, very small, but you see a little bit of a ripple at twice the frequency of the fringes. And for that reason, normally, if I'm doing phase shifting, if I'm doing a measurement, instead of putting in tilt fringes, you try to fluff out the fringes. You try to get as few fringes as possible over the pupil so you don't notice this effect. Now, how large is this effect? Well, it depends on the algorithm you use, and it depends upon how large the phase is off by. And for this particular example, I picked this Schwider-Hariharan 5-step algorithm that we saw previously, because it's really very good. It's much better than just using the 4-step algorithm we derived in class. We'll derive this particular algorithm in a couple of minutes here. But for this particular case, I put in, for the simulation, I put in a 5% phase error. So that means that the phase shift was 90 degrees plus or minus 5% of 90 degrees. And the error here actually is pretty small. The peak to valley error is 0.003 radians. 0.003 radians. So you might say, well, that's fine. So small, it doesn't bother you. The problem is if you're measuring a surface that's good, and it's a very small error, but you'll see it in the test results. You'll see this double frequency error. I mean, it's so small it probably doesn't bother. It doesn't make any difference in the world, except it will make the customer upset with you that you have that error there, because they'll see it in the data, even though it's not. It's probably so small it doesn't make any difference. So this double frequency error is a real problem. It can be a real problem. And so we're going to worry about how to reduce it. I was going to say get rid of it, but you almost never really get rid of it. You just reduce it below some level where you tend to forget about it. So some of you have used phase shifting interferometers. Have you ever seen this double frequency error? Yeah. It's always there. It drives you crazy. Okay. So how can I get rid of it? How can I reduce it? Well, let's think here for a second. So the errors occur at twice the frequency of the fringes. So if we think here for a second, if I take 2 measurements, where for the 2 measurements there's a 90-degree offset in the phase shift, then the errors are out of phase by 180 degrees. Double frequency, double phase, okay? So I take 2 measurements with a 90-degree offset in the phase shift and then average the 2, then I will tend to average out this error because the errors in these 2 measurements are out of phase by 180 degrees. So isn't that nice? Doesn't that sound good? And so I don't actually have to do the measurement twice. But what I could do is I could do an additional say I'm doing 90-degree phase steps, I can take an additional frame of data. And so I can calculate the phase using frames 1 through n minus 1, and also calculate the phase using frames 2 through n, and then average the two results. And this result does indeed give greatly reduced error due to phase shifter calibration. Now the error doesn't go away completely. It would go away completely only if I had a 90-degree phase shift between the two measurements. And if I had a 90-degree phase shift, then I wouldn't have the error to begin with. So it doesn't go away completely, but it does greatly reduce the error. So everyone follow what I did there? So I liked this so much that I got a patent on this. And I was so proud of myself getting a patent. Until I read, I think actually even before the patent was issued, I read a paper and I found a much better approach. So my patent was, I got the patent, but it wasn't worth much then, because this approach, which is by Schwider, actually works out better. It's maybe not quite so clear as the previous one, but it works out better. So his approach was to average, my approach before was to take two measurements and average the two measurements. He averages the numerators and the denominators of the arctangent function. So what I'm saying is we're going to take two data sets and take them with a 90-degree phase step between the two. So we could do just like we did before. We could just do an added frame and calculate numerators and denominators from the 1 through n minus 1 and the 2 through n. And then he adds the two numerators, adds the two denominators, and that gives him the tangent of the phase. And it turns out this actually works quite a bit better than my patent did. Okay. And so as an example here, we will derive this Schwider-Hariharan algorithm, which, as I told you previous class, I used to call it the Hariharan algorithm until Schwider pointed out to me that he had derived it first in this paper right here. So it probably should be called Schwider algorithm, but I call it Schwider-Hariharan. So let's go to the four-step algorithm that we derived in class. We had that tangent of the phase. It's I4 minus I2 divided by I1 minus I3. Now, if I do another frame of data, then tangent of the phase is given by, so instead of taking 4 frames, I'm going to take 5 frames. I first use the first 4 in this calculation. Here I'm going to use the last 4. And so the tangent of the phase becomes I4 minus I2 divided by I5 minus I3. And if we think here for a second, if these were really 90-degree steps, I5 would be equal to I1, because we've gone through 2 pi. But if it's not exactly 90-degree steps, it'll be a little different. And then using his approach, then we simply add the numerators and add the denominators. So that becomes, well, both of these are I4 minus I2. That becomes 2 I4 minus I2. And this becomes I1 minus I3 plus I5 minus I3. So that becomes I1 minus 2I3 plus I5. And so that's our new algorithm. And I tell you, and if you go to, I go through calculations in these notes that I showed you previously, you will see that this makes a huge difference. And in fact, going from 4 to 5 steps, so going from this expression to this expression, reduces the error by a factor of 10. Going from here to here reduces error by a factor of 10. Now, as I said, I1 and I5 should be identical if we really had 90-degree phase steps, and they differ only because of errors in the phase shift. Now, what we could do, so this is getting 5 steps. What I could do is I could start with this equation now, and I could take another step, an I6, and again I could, go through the same procedure again of adding numerators and denominators, and I could get an even better 6-frame algorithm. And I get that, well then I could add another step, add numerators and denominators. I'm going to get an even better 7-frame algorithm, and I guess I could just keep going. And some people do. But the thing is that if you go through these notes that I keep talking about, going from 4 to 5, if we said reduces the error by an order of magnitude, going from 4 to 7 reduces the error by 4 orders of magnitude. And so we could go from 7 to 8, and 8 to 9, and 9 to 10, and so on. I mean, you really, by the time you get to 7, you really have reduced the error by a tremendous amount. Okay. Well, I mean, things are never quite that good. You always, as you're doing more steps, you're taking more time. As you take more time, more things can change. For example, vibration can come in and begin bothering you, causing more trouble. And so, well, some people maybe go to 10 frames. Depending on your environment, you're probably losing more than what you're gaining as you go to more and more frames. But 5, 6, that's a pretty good number. Okay. I want to say a couple of words about Schwider. We'll go back here. There are a few people who are so good that every paper they write you want to read. And Schwider is one of these people. Schwider is superb. And whenever you see a paper that he's written, you can be sure it's going to be a good paper. And I strongly encourage you to read it. And I passed up a fantastic opportunity at one time in my life, I have to tell you here. That Schwider is, I don't know exactly how old Schwider is, but he's approximately my age, maybe a year or two older. And I first got to know him way back in kind of the mid-70s when he wrote to me, and he was writing a review paper on something or another, and he wanted to use some figures I had published. Well, Schwider was in East Germany. He spent, grew up in East Germany. And so you didn't get to meet him because he wasn't able to attend many meetings. But slightly before the Berlin Wall went down, Schwider was allowed to attend a meeting someplace in Europe, and he never went back to East Germany. And so he escaped. And at that point, he couldn't get a job. And someone, at that point I was running WICO, so another friend of mine told me about that and suggested that I give Schwider a job. And I made the huge mistake of not doing that. I think he would have been a great guy to have hired, and because he is so clever, but I missed a great opportunity. Anyway, he's ended up becoming a professor in Erlangen, Germany. Has done very well. Okay, any questions on this? This is really a very powerful technique for calculating algorithms. And this Schwider-Hariharan has become probably the most famous algorithm out there. Yep.
So the output latencies come from what?
The what?
The double frequencies that you're talking about?
The double frequency it comes from almost many sources of errors, I would say. But the one we're talking about here is that I'm using an algorithm that assumes all the steps are 90 degrees. Let's say they're 89 degrees. Then in my phase calculations, I will be introducing an error that turns out to be double the frequency of the fringes. So that's a case where you see double frequency fringes. If you have detector nonlinearity, quite often you get double frequency errors there too. Sometimes it's 4 times the frequency error. If you have any vibration, of course vibration is really causing the phase shifts not to be right, you'll see the double frequency errors. It's probably the most common error you'll see in phase shifting. But it's just, I mean, whatever the phase shift is, we could have an algorithm that was perfect for that if we knew what it was. But if we're assuming it's 90 degrees and it's not 90 degrees, we end up with that error. It just turns out to be double frequency, and it's almost exactly a sinusoid, it turns out. And it's true essentially any algorithm you use. I mean, this makes the amplitude less. If I go to 6, 7, 8 steps, it's even less, but there's still that double frequency. And so for that reason, you generally will fluff out the fringes if you can when you do phase shifting, so you don't have, you don't have the tilt fringes, so you don't see the double frequency. Did I answer your question? Okay, well, so the 2 biggest sources of errors we have are stray reflections and having incorrect phase shifts. And the phase shifters nowadays are really very, very good. And so often the problem why you have incorrect phase shifts is that you have vibration. And so you're taking these frames of data at different times. And so if you have a vibration present, then that's going to make the phase shifts between the different frames different from what you want. So solving, getting around this vibration problem is very, very important. And what I want to talk about here are, I guess I have 7 different ways of getting around the vibration problem. Some of these ways are better than other ones. And of course, I saved my favorite ones to the end here. But I want to go through these 7 different ways of getting around the vibration problem. And, probably the most serious limitation to phase shifting interferometry and in using it in manufacturing environments would be the vibration. And as we said, the vibrations cause incorrect phase shifts between data frames. And the error that you get depends upon the frequency of the vibration, the phase of the vibration, and I guess I don't say it, but also the amplitude of the vibration. And if you go to the literature, you'll find lots of papers on what happens when you have vibration and phase shifting. And they talk about ways of analyzing it, but it's very, very complex. And what we really want to do is just fix this vibration problem. So what are the best ways of fixing this vibration problem? Well, one is you control the environment. You look around this building and how many Newport isolated tables do you find? I mean, you have lots and lots of them. And so people spend millions and millions of dollars trying to control the environment. I mean, air turbulence is another problem. You try to cut down on air turbulence, you try to get rid of the vibration. If you're looking at something as small, then maybe you can put it on a table and get around the vibration. But if you're testing large optics or testing something on the polishing machine or something, it's very hard to control the environment. And so while that's an approach, and that's probably the approach that people have been using most often, it doesn't always work. And I think back to the days when I was running WICO, and we sold thousands of phase shifting interferometers and shipped them all around the world. And almost every time we sold a phase shifting interferometer, included with that was a vibration isolation table. And we still had trouble with vibration. And the problem was that maybe the table wasn't floating right. Maybe the customer would put the computer on the table too, and the computer had a fan in it, or maybe the cables always had cables. I hate cables too. I say I hate mechanical things. I hate cables even worse. But you have to have cables. Someday you won't, but still you have to have cables. And somehow they will couple in vibration. And if I look back in the WICO days, the biggest problem we had with any of our equipment really was the vibration. We could set it up so we didn't have vibration problems, but sometimes the customer wasn't as careful and didn't realize the importance of it. So you try to control the environment. Maybe you make common path interferometers, and we haven't really talked about common path interferometers yet, but we will. So what I mean here is that the test and reference beam travel pretty much the same path. And so whatever vibration we have in the test beam, we have about the same vibration in the reference beam. And so this is an approach, and we'll talk about some of these later in the course, but it's kind of limiting. You take the frames faster, and that helps. But if you have large data arrays and stuff, it's often hard to take the frames faster. So you can measure the vibration and introduce a vibration 180 degrees out of phase to cancel the vibration. And I'm going to show an interferometer that we built using that technique. And it actually worked pretty nicely, but it's pretty complicated. Then we get to what I think are the best ways. And that is, so far when we've been talking about phase shifting, we're taking the various frames at different times. Can we some way take all the frames at once? And it's kind of funny, phase shifting came about in the 60s, late 60s, early 70s. And it really was just, for the most part, until just a few years ago, everyone was taking the frames at different times. But now we can come up with ways of getting all the frames at once, and so we're going to be less sensitive to vibration. And this is probably the best solutions to this problem. And so we'll talk about 4 different ways of doing that. Okay. Well, the first technique I want to talk about here is a technique that was developed here at the University of Arizona, and I think it was Roger Angel's idea originally, and he had a graduate student, an optical sciences graduate student here, Peter Brzezinovich, who did his PhD on this. So this is what we're going to call a 2+1 algorithm. So it's a 3-step, 3-frame algorithm. And the idea here, what Roger came up with, Roger came up with this where making large mirrors over in the mirror lab, and vibration was a problem. How can I get around this vibration problem? Well, Roger's a real expert on CCDs, and so he used some knowledge he had there to come up with this approach. So what he said is, we have to have 3 steps, and so we can take 2 frames of data that differ by 90 degrees, and we can take them real fast. In a second I'll say just how he does that, but we can take these real fast. Now we need a third measurement to kind of get the average. of the intensities, average of the interferograms. And so that third interferogram is taken when we have two interferograms, actually, that are out of phase by 180 degrees. So we don't see the interference, we're just going to see the average intensity. And from these three measurements, then, we can calculate, and it's just that three-frame, I don't know if I mentioned it here, no, I don't show the equation, but many slides ago we had an equation for 3 steps, and that's really this right here. So how do we take two 90-degree phase, two frames that are shifted in phase by 90 degrees, how do we take these real rapidly? That's where Roger's knowledge of CCDs came to play. He says that if we have an interline transfer CCD, we can get these two frames of data real fast. And in the interline transfer CCD, each photosite has next to it an adjacent storage pixel. And that these storage pixels are read out to produce our video signal. And so he will take an exposure real fast. You transfer the charge in the active pixels to the now empty storage sites, and you take the next frame of data. And then you can read out these two frames much slower. So in between the collection, and then you shift real fast the data into the storage. Maybe it's only a microsecond or so, and you can take a second frame. So we're taking the two 90-degree phase frames, maybe a microsecond apart, and then later we can take these two interferograms with a 180-degree phase shift. And then we use that same algorithm that was on a previous slide for 3 steps. So he had to have a way of doing the phase shifting real fast. And this is his approach. You can invent other approaches, but this is the approach that Peter used in his PhD. So he had a laser here, okay? And he then sent the beam out here into, split it into 2 parts here. And these 2 parts will have orthogonal polarization. So we have a polarization beam splitter. This little thing here is a polarization beam splitter. And what Peter did was he had a rotating turntable here with 2 right angle prisms on here. So this is rotating around here like so. And so this beam coming in here, as this rotates, this path is going to become longer. Okay. And so this frequency would be downshifted. This path up here will become shorter. And so this beam will be upshifted in frequency. So the net result is coming out here, he has these 2 beams, orthogonal polarization, and the 2 beams have different frequencies because one beam is upshifted and one beam is downshifted in frequency. Doppler shift here. And then he had a Pockle cell here that would select which of the 2 beams came out. So one polarization would come out, he'd make an exposure, in a microsecond or so he would transfer the data into the storage sites right next to the pixels, and then the Pockle cell would let the other polarization through. And the interferometer had to have a path difference in it, and it had to have the appropriate path difference such that the 2 frequencies here would introduce a phase shift to 90 degrees. Okay. So now he's gotten his 2 sets of data 90 degrees out of phase. Then, sort of at his leisure, he will double the speed of this turntable, And so he'll get not a 90-degree phase shift between the two, but he'll get a 180-degree phase shift. And with his Pockle cell, he will allow both polarizations to go through. So he has two frequencies that are going to produce a 180-degree phase shift. They're present at the same time. And so now he's getting his third exposure with the two sets of fringes 180 degrees out of step. So I don't know, it seemed a little complicated. And I was on Peter's dissertation committee. And I thought this was maybe a little complicated approach, but it worked pretty well. Worked pretty well. You had to have a fairly large path difference, but he was able to get pretty good data this way. So, I mean, this approach, unfortunately, has not been used very much. And the real problem is that you're using only 3 frames. And the problem with 3 frames is that a very small error in this 90-degree phase shift gives you a lot of error in this double frequency error that you get. And so, I mean, they made it work. They made at least one mirror, one large mirror using this approach for testing it. But you really have to be careful, extremely careful in getting the 90-degree phase shift just right. So any questions on how this works? If you go to this other set of notes, I derived this 3-step algorithm, but it's a pretty simple thing to derive. Okay, so that's what we call the 2+1 algorithm. So, as I said, during my days of doing WICO, vibration was always a real headache. And after I sold WICO in '97 and came back to the university, I decided I really wanted to come up with some way of getting around the effects of vibration. And so one approach that we used was this approach here, and this particular system was made by a person by the name of John Hayes here working for me. And it's a complicated approach, but let's kind of look at what it is. So the idea here is that we're going to measure how much vibration we have, and then we're going to introduce some vibration to cancel it out. And so I'll show it here for a Twyman Green interferometer, testing this mirror. And polarization beam splitter. And so we're sending one state of polarization to the reference and the orthogonal state to the test. And we use the trick of the quarter wave plates to convert. So what's reflected the first time will be transmitted the second. What was transmitted the first time will be reflected the second time. So we have 2 beams coming out of here. Test and reference, which have orthogonal polarization, and we put in a polarizer to get interference down here. Okay. We put in a little point detector here that is a phase sensor, and I'm not going to describe right now how that phase sensor worked, but I have a slide coming up in a few slides that will show just how this little phase sensor worked. For right now, let's just assume that I can measure the phase difference between the 2 beams at a point. Not across the whole pupil, but at a point here. And then I'm going to use regular phase shifting to get the measurement over the whole area here. So the output of this phase sensor is going to go back to a modulator, an EO modulator, that is going to introduce a phase difference between the 2 orthogonal polarizations. So I control a little voltage here that changes the phase of the reference beam relative to the test beam. So what I'm going to do here then is, if I have vibration, these fringes are going to be jumping around. And I'm going to see that from my phase sensor. And so I'm going to feed back a voltage here that will adjust the phase difference between the two to stabilize the fringes, to get rid of vibration. Now, the only vibration I'm getting rid of is sort of a piston here. If this mirror is tipping and tilting, I'm not correcting for that. I could have done that, but the main problem we were having was just this thing is moving back and forth. And so that's the error we're correcting for, the piston. So what we're going to see in the next view graph, next slide here, will be the interference fringes with the feedback loop turned on and with it turned off. So with it turned on, the fringes are pretty stationary. Now I turn the feedback loop off, and the fringes are vibrating so much you don't even see what the fringes are. We'll see it again here in a second. There. So now the fringes are completely washed out. I turn the feedback loop back on, and it becomes stabilized. Okay. So this system, any questions on how this worked? I have to admit it worked better than I thought it would. And with this EO modulator and stuff, we could go up to many hundreds of megahertz vibrations, and not that you had to worry too much up at that high, but it really worked well here in the optics shop. So in a sense, I was excited because it worked so well, but it was so complicated and so expensive that I said, you know, what I really was looking for was a product that we could sell lots of, and I decided this is just not it. It's just too expensive. Yes?
With that approach, could you not have to use a vibration table?
That's right. You could do it. You could set that up. You could have the interferometer sitting here. We could have the mirror sitting on your desk. And in fact, I mean, that's essentially what we did for this. If I can get it, come back here. What we did for this case without any vibration. So that's nice, but I don't know. The system was just too complicated. Well, anyway, my time's about up. So what I'll do in the next class is I'm going to talk about other ways of solving the vibration problem. And we'll finally get to something that I think is really very, very good. Now, I said at the beginning I will not be here on Thursday. I'll be in Cleveland, I guess, on Thursday. But I'm going to record the next lecture at 2 o'clock today. If anyone's available, you can come. It's going to be next door. If you can't come today, you can come here on Thursday and you'll see the recorded lecture. I'll be back next Tuesday. I hope. I'm traveling on American Airlines, and everything I'm reading about American right now is not good. A lot of cancellations. So I hope to be back next Tuesday. I should be back next Tuesday. And there's homework to pick up here. And we won't say anything about football.